The final topic we're going to discuss is another type of spectroscopy that has been enabled by lasers because it requires a very bright light source. Raman spectroscopy is a type of spectroscopy that can be done with other types of light, but the key thing is that they must be very bright because it itself is a very weak process. So most of the types of spectroscopy we've been talking about involve either absorption or emission of light. And Raman spectroscopy is a little bit different because this involves scattering of light. And the idea here is that we have light that comes in, hits our sample, and we see light that gets scattered in different directions. And most of the light we see is, and you've observed plenty of light scattering in your life. Every time you look at the sky and you see it's blue, that's because of scattering of light from the sun off of molecules in the atmosphere and particles and aerosols and whatever else. Most of the light scattering that happens is what's known as Rayleigh scattering, where you get, if you have frequency 1 coming in, you get the same frequency coming out. So you get the same color present. And I've got a picture. I haven't put it into my whiteboard here, but as an example of this is a picture from grad school. I didn't take this one, my friend did. But so this is lasers with some liquid nitrogen to get some droplets in the air. And you can see lots of light being scattered off of those water droplets in the air. And we have a green laser and a red laser that are present, and both of those are scattering the colors that they, I guess orange, they're scattering the colors that they are generating, right? So you have the same color as the incoming light is being scattered off of these water droplets in the air. All right, let's switch back over here. So that's an example of Rayleigh scattering. What we're interested in, though, instead is the vast majority of molecules, vast majority of the light that's scattered does this. But about 1 in every 10,000 molecules, 1 in 10 to the fourth, changes energy. And this is known as Raman scattering. So after hitting a molecule, so new one comes in, it hits a molecule, and the molecule exchanges energy with the photon. And we get a different color of light that comes out. So it'd be like sending in your green laser, but you see blue light come out, or probably more likely you'd see red light come out. Right, and so this is what's known as Raman scattering, and we can use this Raman scattering process to make observations about the molecules that are interacting with those photons. The photons are not absorbing the light exactly, they're scattering it, but you can still observe because they're interacting with it. And so there's kind of 3 different possibilities if we're thinking about light scattering. I'm simplifying here, there are more than 3 possibilities. But if we have a light coming in and we have our set of our molecule, we can generally this Raman spectroscopy is used to observe vibrational states, so it's complementary to infrared spectroscopy. So say we have our molecule with different V levels, V equals 0, V equals 1, V equals 2. And up here we have what are called virtual states. So these are not actual states of the molecule, but we kind of use this to understand what's going on. So Rayleigh scattering is our molecule the light comes in, our molecule goes up to this virtual state that's, we add in the energy of our photon, but then it goes right back to exactly the same energy level. And this light that we use is usually visible radiation. Right, and so we see no net change, and this is the sort of scattering that I showed in the previous picture. And then with Raman scattering, there's actually 2 different types of Raman scattering. There's what's known as Stokes scattering, where the molecule starts in a lower energy state, scatters, goes up to a virtual state and goes down to a lower state here, but it goes down to a different lower state. So it goes from V equals 0 to V equals 1. So our photon that comes out has less energy than it started with. So it gave some energy to the molecule. And then the other possibility is what's known as anti-Stokes scattering, where our molecule starts in excited state and goes down to a lower energy state. So the frequency of our photon coming out has more energy than the photon that went in. And so we can use this to measure, this difference in, right, the difference between the energies of our two photons tells us what's the difference in energy between these two different vibrational levels that are observed.